Right? So these are our exceptions to the octet rule. The ones that have less than 8 electrons, pretty easy to remember. Hydrogen, beryllium, boron, nitrogen, right there. Essentially all of the elements between hydrogen and carbon um, that either A, don't have a full subshell, like helium, is 1s subshells full up, and B, are metals, like lithium. Lithium's a metal. He's not going to behave covalently very often. And so all of those are okay with less than 8 electrons. And then there's a whole bunch of elements that are okay having more than 8 electrons, with this caveat that they have a central atom with empty d orbitals. Okay. So we're going to do a handful of examples, and sort of like we did in class on Monday, I'm going to give you a minute to try it on your own, and then I'll come back and we'll work through it together. Okay. So aluminum triiodide. I told you a little bit ago that aluminum very rarely behaves as a nonmetal. We could go back and look at the electronegativity difference between aluminum and iodine, but because iodine is relatively in the middle in terms of electronegativity, and aluminum is too, when these two elements in particular combine, they often combine in a covalent manner rather than in an ionic manner. Okay? So I'll give you a minute to draw that Lewis structure for aluminum triiodide. Remember, he's just below boron. Oops, sorry. How many valence electrons in aluminum triiodide?
24.
That's it. I've used 6. We know how this goes. Okay. So that's aluminum triiodide. Again, aluminum only rarely participates as a nonmetal, but here's one of those examples where it does. Now, in reality, aluminum triiodide doesn't really exist in this form very much. What happens is, because it really would like to have a complete octet, right? Aluminum and boron are different enough that aluminum really does want a complete octet. Many times aluminum will form a compound that looks like this, where you take 2 of these Al-I3 groups and you combine them together to get Al2I6. And if you do it this way, aluminum gets his full octet. Everybody has a full octet, but the aluminum has 8 electrons, and that octet rule is satisfied for aluminum. Now, if we did some formal charges here, we would discover that aluminum has a -1 formal charge and iodine has a +1 formal charge. So not ideal in terms of electronegativities, but it's sort of a balance between, do we care more about electronegativity and formal charge, or do we care more about having a full octet? And so this aluminum triiodide can exist either as the single unit or as this double unit that we call a dimer. Okay. Now, I do not expect you to be able to know, oh, aluminum triiodide, that's one of those molecules that can form a dimer, right? I'm just giving you an example of a molecule that sometimes behaves one way and sometimes behaves another. Okay. All right, phosphorus pentafluoride, where all the F atoms are bonded to the central P atom. Phosphorus pentafluoride. How many valence electrons?
40.
Yep. We've already used 10, 16, 22, 28, 34, and 40. Right? So there's our PF5 molecule. Right? Notice we've got 10 electrons around phosphorus. What subshell is phosphorus in?
P?
The P subshell, but which P? N equals
3.
N equals 3. So he's in the 3p subshell. That means he's got those empty 3d orbitals that he can push extra electrons into. All right, a couple more. The sulfate ion, in which all 4 oxygen atoms are bonded to the central sulfur atom. You can only give me one resonance structure for this. There are multiple resonance structures, but just one resonance structure for now. We'll talk more about this one in particular tomorrow in lab. All right, so how many valence electrons are we working with?
32.
32 electrons. How many double bonds did you end up with in your molecule?
1.
All right, so let's go ahead and fill in our electrons. So 1 double bond. Here we've used up all 32 of our electrons. We've got 10 in bonds and then another 22 in lone pairs. I'm going to quickly do a calculation of formal charge. Right? So all of our singly bonded oxygens, I'm going to represent here. They start with 6. They have 6 non-bonding. They have 1 bond. That gives them a -1 charge. Our doubly bound oxygen starts with 6, has 4 non-bonding with 2 bonds. That's 0. Remember, I told you oxygen likes to make 2 bonds. He's happy there. Sulfur starts with 6. He has no non-bonding, and he has 5 bonds. That leaves him at +1. And overall, we have a +1 and a plus, sorry, these are -1s. We have -1, -1, -1, +1. And since he's an ion, he really needs his bracket and his 2 minus. And so do all of our formal charges add up to the overall charge of the ion?
Yes.
Yes, they do. However, are they as low as they could possibly be? Well, because I've got a -1 and a +1 right next to each other, that's always an indication that I could form an extra bond and reduce both of those formal charges. So I'm going to erase these two, and I'm going to erase this lone pair. And if we look real quick, I'm going to draw this one in a lighter blue. If we do this, well, we've already done the formal charge for that oxygen, double bonds. He's 0. And now I'm going to do sulfur again, right? He starts with 6. He's got no non-bonding. And now he has 6 bonds. And so sulfur is now 0 as well. And so this is a better Lewis structure because we have gotten as many atoms to have a formal charge of 0 as possible. Right? And so, you know, we good that you decided to push in one of those to have an extra bond, so that we did reduce the formal charge of sulfur from +2 to +1. But whenever we have a positive and a negative formal charge next to each other, we can try to form an extra bond and see if we can change those formal charges to 0. All right. Tomorrow in lab, we'll draw all the resonance structures for this guy. All right. Last one for today, a Lewis structure of the noble gas compound xenon tetrafluoride. So we talk about noble gases not reacting very much. Right? It turns out that as noble gases get bigger and bigger and bigger and bigger, they have less and less idea of what's happening to those electrons that are very far away from the nucleus. And sometimes those electrons are pulled away by very electronegative atoms, right? Remember, fluorine is the most electronegative atom that we have. And so he is using all of his strength to pull some of those electrons away from xenon. Now, he can't pull them away in terms of becoming an ion, but he can pull them away just enough to share them, right? And so there are a couple of compounds that do exist with noble gases, but they only exist with very electronegative elements. Okay. So it tells us that xenon is the central atom with some fluorines around it, xenon tetrafluoride. So I've got 4 Fs. I'll let you go ahead and work on that Lewis structure for a minute. All right, how many valence electrons in xenon tetrafluoride?
$18. Oh, sorry, 36.
There we go, 36, sounds good. 36 electrons. We've already got 8 drawn. So there's 14. There's 20. There's 26. There's 32. Everybody has a full octet, and I have nowhere else to put my extra electrons. My Lewis structure rules say that I fill up the octet of the peripheral electrons first, and then what do I do with any leftover electrons?
Going on the central atom.
They go on the central atom, absolutely. And so I put a pair of electrons there and a pair of electrons there. Whenever we add electrons in Lewis structures, remember, we always add them in pairs rather than adding them individually. Of course, except if we have an odd electron species like NO that we saw earlier. Okay. So xenon is in the, I don't have a periodic table in front of me. I think xenon is the 5p. And so he certainly has some D, and he even has some F subshells empty that he can put some things into. And so right now he's got 12 electrons around him, 4 bonds, that's 8, and then 2 lone pairs for another 4. So he's got 12 electrons. I think 12 may be the most that I have seen around a non-metal. So if you see something with much more than 12, you should be concerned. All right, any questions drawing these Lewis structures for expanded octet species? All right, hearing none, we will adjourn for today, and tomorrow in lab, we will work on drawing Lewis structures and making sure that we have this concept of atom connectivity down pat, okay? I hope that you have a good Wednesday.
Thank you.
Yep.
Dr. Davis,
Yes.
my laptop kicked me out and I just rejoined on my phone, but then has class been dismissed?
Yeah. So we just did a couple more examples. I will upload this video to YouTube so you can catch the tail end of the lecture. But we just did a couple more examples of compounds that have expanded octets.
With the xenon tetrafluoride, was that the last example?
That's the last one we did. Yep.
Oh, okay, perfect. I got that. All right, thanks, Dr. Davis.
Sure. Have a good one, Lily.
You too. Bye.
Bye-bye.
Hi, Dr. Davis. So would you be willing to go over what our quest will be covering? Is it just over the Alex?
Yeah. So we are going to have sort of the tail end of chapter 8, right? So we the quest didn't cover any of chapter 8 last time. And so in chapter 8, we talk about atomic size, we talk about ionization energy and electron affinity. So those 3 trends, be able to not only know what they are, but be able to talk about the trends and use those values, especially for ionization energy and electron affinity.
All right. And I actually didn't understand the sulfur tetra